so there were a very interesting discussion in Shimo's talk whether the Novikov conjecture is a problem in topology or algebra. So I guess I will try also to argue that it's also a problem in geometry and analysis. And okay, so to make that connection, I will start with, well, the Dirac operator, and which encodes the information in like geometry. Of course, it's also an object in analysis. So the Dirac operator is in some way, it's just a square root of the Laplacian operator here. So it's a very concrete. When n is 2, see, we can take the coefficient like C1 to be like just -1, 0, 1, 0, and C2 to be like I0, I0. So it's a very, with this coefficient, you can see that the square is just the Laplacian. Now, in high dimension, it's a little bit more subtle. You need, well, the most efficient way of creating those coefficient matrices is by so-called Clifford algebra. And of course, I avoided the issue on which Hilbert space this operator is acting on, and that's a crucial issue. And I would just like to mention that it's like the minimum possible space on which this operator can act on. Okay. Now, so I also would like to mention that in the computation that the square of this Dirac operator is Laplacian, we use this like fact that the second order partial derivatives they commute. I think this is called Guoliang theorem. So my son is taking multivariable calculus, so I think that's the name. So okay, so this is used in a crucial way. Okay, I want to emphasize. And so now with this, actually you can generalize this construction to manifold. We need a global like orientability condition called spin, which I'm not going to mention it. And so now we can ask the same question, whether the square is Laplacian or not. And we run into the same issue, whether partial derivative like commute or not. And that's, so of course we replace partial derivative by covariant derivative. And so this is asking the question whether, something like this is zero or not. But we know on general, like Riemann manifold, and this is not zero. This is exactly information about the curvature. So you expect there's a collection term which is about curvature, but then you sit down and compute. It's a chord of curvature. So whether curvature like appear or not, that's not mysterious. But and the interesting thing is we get the scalar curvature. Okay, all right. So now from here, because the Laplacian is non-negative, so if the scalar curvature is positive, then the Dirac operator is invertible. Okay, so this establishes a connection between like positive scalar curvature and invertibility of the Dirac operator. Okay, so then of course a natural question is how can we decide if the Dirac operator is invertible or not? And that turns out to be like what the central question in operator theory. So I mean, in finite dimensional case, whenever we have a linear transformation, we know how to decide whether it's invertible or not just by computing the determinant. But this is in the infinite dimensional case, we don't have such a tool like a determinant. Okay, so it turns out the most efficient way of deciding whether it's invertible or not is by studying another invariant called the index invariant. Okay. So the index invariant is just, well, let's first focus on a closed manifold. It measures the size of the kernel and the co-kernel. Okay. Now, of course, if the operator is invertible, both kernel co-kernel are zero. So this is this entire invariant is zero. Now, why do we want to like take the difference? And so it makes, by taking this difference, it makes this invariant very stable. So if you make a perturbation, like if you deform the Riemann metric, this would not change. And that's a very remarkable fact. And that makes this index like to be, well, I consider this to be one of the most beautiful invariant. So there's a lot of stability. Now, it is actually precisely this stability which allows us to like compute this. And that's, of course, the famous the single index theorem. And this heterogeneous is computed by, can be just like L class in Schmoll's lecture, it can be computed by information from the tangent bundle, okay? In particular, you know, we have this remarkable consequence. And if a manifold has a positive scalar curvature metric, then the genus, that's zero. That's a topological, differential topological invariant. Okay, so that's a very remarkable fact. And okay, so now they are more refined index invariant, so which I'm going to talk about next. So let's first just look at a very simple case, okay? And let's have a manifold with, say, with like a fundamental, we can think about the simplest case, a manifold whose fundamental group is finite, and then the covering space so has a natural action of the fundamental group. Now, in that case, still, you know, we can talk about the Fredholm index of the Dirac if we lift the Dirac operator. I think I should probably look at the lifted operator on the covering space. Okay, so then, of course, you can talk about the Fredholm index, but there's something more refined. You look at the kernel, co-kernel, which are finite dimension, and they, because the tilde commutes with the finite group, so the kernel and the co-kernel, they are representations of this finite group. So if we view these as representations, and then they live in the being group of representations, and that's a much more refined invariant. For example, the classical, well, the previous Fredholm index can be zero, but as representations, it still can be non-trivial. Okay, so this so-called equivariant Fredholm index, and it's a more refined invariant. Now, a natural question is that, you know, can we? So I mean, in most interesting cases, the fundamental group may be an infinite group. Can we make sense out of this? Okay, that's what I'm going to introduce next. And of course, that touches on the question, you know, about representation theory of infinite discrete groups. That's, you know, in a way, that's a subject which is not much is known. Okay, for that purpose, I'm going to now introduce something which probably not, especially for geometers, it's something we don't use. Okay, just to make precise of the idea of what representations of infinite groups we are going to consider. So we are going to look at this so-called group algebra, and that's a very simple object. It's just a way of turning a group into an algebra by taking formal linear combinations with coefficient in the complex numbers. So this is a finite sum, okay? And of course, we have multiplication, we have addition, you know, so it's an algebra, okay? All right, so but we are going to complete this. So complete this in two different norms. The first one, I'm going to we will represent this, each of the gamma as a unitary operator. So that's called the regular representation. Okay, so what it does is that on each like function, and you just translate. So this is called the regular representation. Okay. All right. Now, so for each gamma, you represent this. This is, of course, a so-called unitary operator. It preserves the norm. Now, for linear combinations, it's a bounded operator. So there is an operate norm, and that's that's the operate norm of. So with respect to this called regular representation. Okay. So we complete this. That's called the reduced group system algebra. But actually, for something for some technical reason, which I need at the end of the talk, I'm interested in so-called maximal system algebra instead of just completing it with respect to the the regular representation. I consider all possible representation. I consider the norm, so this is a so-called maximal norm, and that's going to be the set of all possible star representation, or possible unitary representation. Let me put it this way. Okay, phi is a representation. So of course that norm is bigger than this. Okay, all right. Okay, now to make sense about representations, I use the language of K theory. So K theory, so I'm going to just focus on K0. K0 of this group system algebra or any other algebra is just the abelian group generated by or idempotent in the matrix algebra. So matrix algebra with entries in this algebra. So an idempotent is just an element whose square is itself. Okay. Now, the reason this is interesting is that, like in the case of finite group, this is exactly the abelian group of representations. Okay. So in general, the K group is, we consider this to be the abelian group of like unitary representation of gamma. Now, of course, this group can be different. Depends. So that's a kind of subtle issue depending on which norm we choose. Okay, but let's look at like groups like Shimo mentioned in his talk, like for example Z2. Then what is this group system algebra? This group system algebra is actually it's the dual space because all representations are parametrized by the torus, the T2. So an idempotent, oops, I actually don't like this color. An idempotent in here corresponds to a vector bundle on the T2. Because what is the idempotent? The idempotent is just the projection from the trivial bundle, in which it contains this vector bundle to the vector bundle. So it's like very, very geometric. So, okay. All right. So now once we make precise the idea of like representations in terms of K theory, we can now define high index. Okay. The definition is at the first glance, it looks a little bit technical, but the idea is trying to generalize.
Well, it's important you didn't say in which category. It's a morphism in what category? It is? What kind of method is?
Morphism. Oh, you mean like
I didn't say, no, say it's important. Say square as well, but say set map, linear map, homomorphism, algebra homomorphism. Who is that?
Oh,
you didn't say
this P. Oops, sorry.
Yeah, this piece. Who is he?
P is in Mn of like this star of gamma.
It's homomorphism. In matrix homomorphism.
Yeah, you can say this is a linear map. Yeah, it's
linear map. Okay, it's linear map of algebra. It's not a
It's like let me just spell out. It's a matrix. Yeah. Mn means it's the n by n matrix with coefficient.
It's linear map over this algebra.
Yeah, over this algebra.
Exactly. This is what.
Yeah. So it's here. So, but we allow. Yeah, I should mention this. We allow n to change. So, but in taking this union, my Mn is sitting in Mn plus 1. So by just, if you have a matrix A here, oops, sorry. Sorry. So I probably should, if I have a matrix A, I just embed it into a large, okay? So that's what this union, yeah, well, okay. So this is K theory. Of course, that's a very fast introduction to K theory. Okay. Yeah, I would like to make this talk accessible to, I see a lot of young people. So if you have questions, please interrupt me, okay?
No, but if you don't say who is P, I mean, it's just, no, yes, become everything disappears. You don't know what you talk about, right?
Oh yeah, yes. P is in here. Yeah,
Yeah.
P is in the matrix algebra. Of
No,
course,
no,
that's
matrix algebra over this algebra.
yeah. It's an algebra Mn of C star of gamma. Yeah.
And the map a linear over this algebra.
Yes,
And
exactly.
not homomorphism or anything, just okay.
Yeah. It's just it's a linear element. Okay. Any other question? Okay. All right. So of course, formally we can just define this as some kind of equivalent Fredholm index, but technically that's not exactly how it's defined. So you know, when we define classical like Fredholm index, we are looking at the kernel and the co-kernel. So we are looking at exactly like spectrum 0, okay? But the high index is a little bit more subtle. It encodes information about small spectrum, okay? All right, so with this now, I will try to justify the technical definition, but it's, okay. All right, so we start with a closed manifold. We take the Dirac operator on M. Now we lift it to say the universal cup. All right. So we take like we are the Dirac operator. It's a differential operator. It's unbounded. So we, you know, people in operator theory always like bounded operator. So we will make it bounded. And actually, as an example of this, so we are going to do so-called functional calculus. Okay, of this operator. It's x over square root of 1 plus x squared. Now, I also imposed this condition. Actually, if I take this specific function, it does not satisfy the condition, this particular condition. Let's not worry about this particular condition. I want it back at some point. But in the definition, if I take this particular function, it would work. Okay. So now I take functional calculus, apply this function. That's something actually very simple. If I have this particular thing. Now, I'm also focusing on the even dimensional case. So in this case, my D is like, can be split into D plus D minus. And of course, this square is like just D plus square 0, 0, D minus square. So it's something very concrete. So this capital F, it's just one. So I can put this in the front, and then it's just T plus 0. Oops, D minus 0, 0. So it's this is very concrete. So this is what I call the U, one of them, or call the U one of them. It's just a little normalization, okay? Making it bounded. I'm not doing anything deep, okay? All right, so it's just some language here. All right, so here is a nice idea from K series. So so even in a classical case, an operator, you know, so if an operator is not a Fredholm but not invertible, I'm not able to like make a small perturbation to make it invertible. The obstruction is exactly the Fredholm index. So, and here, in order to do this, like, so U is one, so U and V are joined to each other. So if I put this together, then the Fredholm index would be 0. Then I can make a perturbation to make it invertible, okay? And here is a precise way. This is a clever formula. So you don't have to worry about why I choose this way. This is actually, so U and V, this 2 by 2 matrix may not be invertible, but this is a clever way of making a perturbation. This is actually, this W is a perturbation, a small perturbation of this U and V, okay? But the point is W is invertible, okay? W is almost this. Now, actually, I can define the high index by a conjugation of this invertible element and 1Z, 1, and this element is in the K series of the group system algebra. Actually, to be precise, it's in the tensor product. Okay. Now, of course, you might say, well, this looks a little bit, crazy, this computation. And the best way is to check in the classical Fredholm index case. This indeed gives you the classical Fredholm index. That's actually not hard. Okay, so now let me also explain why this element is in this like group system algebra. So the operator acts on some Hilbert space in M tilde with with coefficient in some vector bundle. Let me ignore the vector bundle. But this is simply if I pick a fundamental domain, let me call this F, and so F tensor with the fundamental group, little L2 of the fundamental group. Okay, so I can decompose the Hilbert space capital L2 on the M tilde into two parts. One is just a fundamental domain. One is the discrete thing, little L2 of the fundamental group. Now, and it turns out that this element and is going to be exactly, lies here. The K is because things like these, elements like this, they are so-called locally compact. So K here is the algebra of compact operators. Okay, so compact operators are just operators which can be approximated by finite length operator. Okay, so this is how this definition works. Okay, is there any question about this construction? It's a little bit technical, but still it's quite natural, actually, not too bad. Okay, so this is the precise definition. This is the precise definition of high index. Okay, and the important thing is that the most important thing is in this construction. This is an obstruction to invertibility, and it's also invariant under homotopy, continuous deformation, just like the classical Fredholm index. Okay. Oh, for the young people who are interested in learning the subject, I want to advertise a book I wrote with my collaborator Rufus Willard, which was just published in last year. We tried to make it very friendly, so in this book. Okay. Okay. Any question about this construction? Okay. So now, of course, what it makes the connection to scalar curvature is Jonathan's vanishing theorem. Okay. All right. So Jonathan's theorem says that if a closed spin manifold has positive scalar curvature, then the high index, actually probably the spin part can be also weakened. Then this high index vanish. Okay, in this K group. Now here is what I want to emphasize the one point. So it's crucial to have this algebra. Okay. Okay, let's outline the proof. The proof is very conceptual. So let's say if it's invertible. If it's invertible, then then there is a spectral gap near zero, right? Okay. So so in the construction, we have a choice of this functional calculus. So if this is a spectral gap here, so I can choose this function. So one here, but it going to transition to -1. It's going to but it's -1 here. Okay, -1 here, 1 here. Okay, so then you see in this functional calculus, if I make such a choice of this little f, then f squared would be, because the part of f which is doing something to the operator is the -1 part, because the other part is in the spectral gap. So therefore, f squared is going to be exactly its identity. So it's invertible. So if it's invertible in this construction, you know, I was trying to choose this W, which is a little perturbation of U and V. So UV is already invertible. If U and V is already invertible and it's diagonal, I can, in this definition of the index, I can choose the W to be this diagonal element. But if it's the diagonal element, this P will be just this matrix because, you know, it's just 1, 0, 0, 1. That's going to be the P. Of course, then, you know, in the definition of this index, we have a trivial element, so it's 0. Okay, so that's the proof. Now, what I wish to emphasize is that when I choose this F to be the way, you know, to avoid the spectral gap, and so I need to prove that, you know, this way of defining the index is independent of the choice of the little f. Okay, now in this in the proof that the two things like can be deformed to each other, so I'm not able to avoid, I mean, this homotopy will be living in this cyst algebra. I'm able to actually, in the initial definition, if I choose my little f to have Fourier transform to have compact support, then I can make the index not to be in the cyst algebra. Actually, I can make the index, this high index, to be just the group algebra tensor K. So that's possible. So I can, so then it's going to, I can define the high index to be a purely algebraic object. So then it's a problem in algebra, okay? But in order to like prove that this, you know, this way of defining high index is independent of the choice of the F, I have to go to the cyst algebra. I actually, there's no way you can keep things in just in the group algebra. So cyst algebra is crucial. There's no way, it's not just artificially here, and we cannot avoid that. Okay, I will actually give another reason that cyst algebra is important. Okay, so this is my first answer to why cyst algebra. Okay, all right. Now, but okay, so once we have this, we are motivated now to well, actually, I'm going to formulate this so-called strong Novikov conjecture. This is more like a conjecture, well, in the context of analysis. So, but I'm focusing on the Dirac operator. So the high index is non-zero. So it's a way, it's an algorithm trying to decide whether the high index is 0 or not. So the conjecture says it's non-zero if and only if the K homology class, which Shimo mentioned, in the K homology group of the classifying space B gamma. Oh, I should not say B gamma is I'm lying. Well, actually, maybe E bar gamma, like in Shimo mentioned this in his talk. Okay, but the reason this is a nice conjecture is because, well, the easy of deciding whether it's 0 or not in the K homology group, that's computable. At least I would say, well, it's Shimo's job to, I can push my job to Shimo. Like, you know, you can compute this. It's about space. Okay, you can use, you know, all the tools, cutting, pasting, stuff like that to decide this. Okay. On the other hand, K-series of like group cyst algebra, that's a very group object, and so it's a local. This is, I would say, this is a local to global like principle, and so we are solving a global problem using something very local. So that's why it's interesting. Okay, let me also mention, if I take, instead of the Dirac operator, I take the so-called signature operator, then it implies the classical Novikov conjecture. So that's why it's called the strong Novikov conjecture. So this is the connection to the classical Novikov conjecture in Shimo's talk. Okay, all right. So now, oh, let me also mention, you know, like Shimo also mentioned the Taurus case. And in this case, you know, actually the classical the classical Fredholm index method does not tell you that torus, whether torus have positive scalar curvature, but if you use this, and then you can compute the high index, it's non-zero. Okay, the classical Fredholm index is zero. Oh, I should mention, sorry. So this is the work of Klimov, Watson in general, and Shine in dimension up to 7. So it, yeah. So actually, this problem, the TN problem, I think if I remember, it was an open problem for many years, 20 years or something like that. Okay, so now just to be encouraging, although we don't have a good idea about counterexamples, so if, I mentioned that the high index can be defined in the group algebra tensor K. And now for this algebra, whether you tensor K or not, the compact operator does not make a difference in K theory. But for algebraic K theory, it does make a difference. And so K0 of like group algebra tensor K, we can also formally ask, whether the Novikov algebraic Novikov conjecture is true or not. Actually, in this case, it's true. It's true for all groups. So there is no condition at all. So I don't know if this, although this has no, but unfortunately has no application to the scalar curvature, as I explained. Now, to prove this, this is the trace method, kind of trace method, not in the spirit of trace method, I would say, Shimo mentioned. Okay, so this would be an entire different. This kind of argument is very different from geometric argument. Okay, and well, maybe from this angle, there is some optimism. The Novikov conjecture, maybe it's just a maybe. Okay, all right. I just want to mention this. Now, well, actually, as Shimo was saying, there was 50 years of Novikov conjecture. It's harder to summarize. I'm not as pessimistic as Michel, and so I would argue that right now. So it's harder to, of course, summarize the current status. I would argue the strong Novikov conjecture is true if a group is from nature. And so, of course, we can argue what is a group from nature. And so there's a lot of work, like, Shimo was mentioned, so many years. I mean, it's a fascinating problem. It connects to a lot of things. And I'm just writing down a list of people whom I learned a lot, but it's an incomplete list. Okay, if your name is missing, yeah, I'm sorry. Please let me know. Okay, so because I think Michel was saying that in this seminar we should explain things from the roots. So I was debating with myself what to talk about, and so I would argue that although in terms of groups the condition varies, sometimes it's not clear which condition contains which, but the method is very, I think the strategy is very coherent. That's what I want to explain. But let me first say where the difficulty is. So the difficulty from the analysis point of view is the difficulty computing K groups of the group system algebra. Now, what K theory, of course, is a cohomology theory. Now, how do we compute K theory in topology? When we have a space, we do cutting and pasting. Okay, here we have an algebra. So to do cutting and pasting, we need in classical case, we need the subspaces. But here we need subspaces in terms of algebra, they're just ideals. But sadly, there are not so many ideals for group algebra. Actually, generically, all those system algebras are simple. Simple meaning that they the only non-trivial ideals is zero all the entire space. So this means that as a non-commutative space, they all kind of glued together. If it's harder to chop them into pieces. That's the difficulty from this point of view. Okay, so now what is the strategy? Here is the strategy. I think I can argue all results are proved this way, can be proved this way for the Novikov conjecture. So what it is that we are going to embed this cyst algebra to a bigger cyst algebra. Okay, I will explain how to do this, such that the big cyst algebra A, the K series is computable. And secondly, this embedding, we don't want to lose the K series information. We still want to retain all the K series information. So from this approach, the Novikov conjecture is more like a computational complexity problem, okay? So how, we want to introduce some algorithm. We want to compute the K series. We want to see if it's, the algorithm will stop at some point. If the algorithm stops, okay, good. So we have our result. Okay, now I'm going to, okay, so now I'm going to introduce how to embed into a big algebra. Okay, so the method I'm going to show does not contain the most general, but this is the idea. Essentially, everything can be done this way. Okay. All right. So here it is. So I'm going to of course, one way of studying groups is let it act on some space. Okay. I'm going to let it act. Well, for simplicity, because a lot of machinery has been introduced, like KK series, cyclic homology, but I want to do something very elementary. And if someone really want to learn it, you can learn it in a few hours. Okay, no machinery. So I want to be very down to earth. Okay, so the group acts on a compact space X. Okay, so I want the action to be like locally proper. Now, if you have an infinite group, of course, it's not possible to act on a compact space properly. Okay, but it turns out you can, a lot of situations, you can make your action to be locally proper. Now, let me explain what I mean by locally proper. So let's see. I want to first explain the idea, like when you localize to a subset, let's see a subset U, an open subset of U of X. And I want to explain the idea, what it means when the action is restricted to U, it's kind of proper. Okay, so let me introduce an equivalence relation. The equivalence relation, for simplicity, I'm going to assume the action is free. If it's not free, we can also explain this. It's just the language is a little bit complicated, slightly more complicated. So 2 points X, Y, and U is defined to be equivalent if there's a finite subsequence of points like X0, X1, and to Xn. Okay. Now, and Xi can be transformed to Xi plus 1. Oh, I'm sorry. So I forgot to mention, I choose a finite subset F of the group. Okay. So I want Xi to be transformed to Xi plus 1 by group elements only from this finite subset. Okay, so when I talked about like locally proper, I only with respect to this finite subset of the group. Okay, so this is the equivalence relation. Okay, now I'm going to introduce like some kind of so-called dynamic dimension of the action. Okay, and this is some kind of computational complexity, like computability assumption. And so whenever, if I can like decompose the space X into like finitely many, like U0 to UN. Okay, the dimension is the smallest n such that for every finite subset of the group, I can decompose X to like n plus 1 number of the open subset such that this equivalence relation on each of the UI has uniformly finite equivalence relation. Okay, so it's like in some sense there's some properties. Okay, so of course this properties is with respect to this finite subset. Okay, so this decomposition also depends on this finite subset. Okay, all right. It turns out if we have this finiteness condition, then I can compute the K theory.
I can give an example. A simple action which you know what is this number.
Okay, so actually the simplest action is Z-axis on the circle with like irrational rotation, but that actually technically I have to do a little bit more. So I will instead I will have Z-axis on. I mean, this does not have to be it can be a hyperbolic group or something. Acts on the stone check compactification. That's a kind of crazy thing, but yeah. So then
it's not free. Come on, it's not free.
That's true. That's true. But actually, but this concept, it's just for convenience. I use the freeness. But this concept makes very good sense.
Okay. So it's not free. Okay.
Yeah, we don't need to have free action. It's
no, exactly. I was thinking it was free. Very hard to have meaningful example for free. If non-free, I can imagine.
Yeah. Okay. I'm just because if it's not a free action, because I need I think the best way to introduce this concept is use a little bit groupoid. I was trying to avoid the groupoid language, but it can be perfectly defined. I mean, there's no problem defining.
No. If there are orbits are dense, if dimension is infinite, what?
If dimension, sorry.
If you have recurrency, if you actually understand your action when there is no recurrency, but if it's recurrent action.
Yeah, just locally has no recurrence, but it's with respect to a finite subset of the group.
No, but you need finite dimension, right?
Oh, yeah, it is a finite dimension. Yes, I need like local. Yeah, I need the finite. So this is like yeah.
But so recurrent action may have finite dimension.
Yeah. Yeah, it might have finite dimension. Yes.
Even recurrent action.
Yeah, recurrent. You mean like
the dense orbit?
Yeah. That's possible. Like the circle, like the axis on the circle. By irrational rotation.
Irrational rotation.
Yeah. That has asymptotic dynamic dimension 1 actually.
Mm-hmm.
Yeah. Okay. Okay. So I actually those method. Actually, the idea can be, one can learn this method in a few hours instead of other machinery like KK or stuff like that. So this method is introduced in this paper over my with Eric Gantner Lofus. It's on arXiv. Wow. But I will explain the idea. Okay, it's very simple. It's like very elementary. Okay, so in order to implement this algorithm, we have to introduce something, some kind of quantitative K theory. Okay, so this is where quantitative K theory, because to match the choice of finite subset. Okay, so the most natural language is to like put a proper length function. So I mean, such a length function always exists on our group is countable. Okay, all right now. So you can measure the length of like something in a group algebra by just taking the length, the sup of C gamma not 0 and the length of the group elements. Okay, so you can extend this length function to this to only find a sum of the C algebra. Okay, all right. Now the quantitative K group is a abelian group generated in connection to positive scalar curvature. Our idempotent have to live in the C algebra, but we can do an approximation. After an approximation, they live in the group algebra, but we lose something. They are no longer idempotent. They are also called quasi-idempotent. So that's like square is not exactly itself, but the norm is very small. Okay. So let me say 1 over like 100 just to be sure. Like, and also actually we need to control the norm. Well, if it's almost a projection, then it's almost 1. But let me say put 10. Okay. Okay. So it's something like generated by so-called quasi-idempotent, but we want to control the number of group elements involved. Okay. So if my scale is R, then only like group elements with whose length at most R is involved. Okay. So this is the so-called quantitative K group. Okay. Now, how is this related to the usual K group? You just take the limit when the scale goes to infinity. So you can recover the general K group. Okay, so here now, so how is this useful? So in the algorithm, I was like splitting up to like to split up to open finite and many open subset in order to, in case the K theory world, to do such a splitting, like you need to use those quantitative K group. Otherwise, in the framework of just usual K theory, we don't know how to split. Okay. All right. So this is why we need this, more refined version of K theory to provide an algorithm of computing K theory. So this is really so if it's some kind of quantitative version of Merville-Torrey sequence, you cut it into pieces, and so the finite dimension is there, just you allow the algorithm to stop at some point. Okay. So from this point of view, I would like to think the Novikov conjecture in a way, it's a computational complexity problem. In this kind of world, you see this scale R, each time you do a cutting and pasting, the R has to increase a little bit. It's like in the summertime we bring a watermelon home. You have a knife. The knife is not very sharp. It's kind of dumb. Each time you cut, you lose a little bit. But if you don't lose too much, then you can put back the watermelon to see how it looks like after cutting into pieces. But if the knife is like, yeah, if you don't have those dimensionality condition, then you might destroy the whole thing. Okay, so this I think there's a similar issue with LCM. Okay, all right. So, but I want to also there's one nice connection to scalar curvature, this quantitative thing. Okay, so especially in Michel's recent paper, articles,
Excuse me, low battery.
Yeah, so it became like an important issue that to estimate the low bound of scalar curvature. So this is like in this article with Hao and Zhang, we showed that if you have like a K0, positive K0, and they exist not zero, that such that if the scalar curvature is greater than or equal to K0, then the index already vanished in this the quantitative K theory of this scale. Okay. Now this can be interesting because we can also introduce a quantitative version of the Novikov conjecture for for Dirac operators. So you can, whenever you can prove that, so vanishing like in the K homology, it's not in the final classifying space, but in some scale. So a lot of times it's not zero there. Although in the final classifying space, it's still zero. Okay. So it gives you some kind of rough estimate from this kind of estimate. Okay. And also let me mention that this kind of algorithm I was mentioning that actually tells you how to prove a quantitative version of Novikov conjecture. Okay, any questions? So it's more like I did not like write down like a list of existing results. There are many interesting ones, but it's more I want to explain the spirit, how to prove things. Okay, and I also want to emphasize It's actually very, very elementary. Okay, can be very down to us. Okay, it does not have to learn all the machine learning. Okay, so now I would like to talk in the last, how many minutes? I have about 10 minutes. I would like to talk a little bit about my joint work with Shimo and Zhang. Like I want to actually propose something called Novikov conjecture at infinity, which is also related to a question Michel proposed in scalar curvature. Okay, all right. So let me just quickly explain what it means. Okay, so now the reason I introduced the maximum group system algebra is that there is more functoriality. So if I have a group homomorphism from G to gamma, then it induces a homomorphism for the maximum group system algebra. But that's not true for reduced. Okay, all right. So now if I have a homomorphism from a group G to gamma, actually I can introduce a so-called relative group system algebra. So this is defined by it's a mapping cone construction. Now this mapping cone actually fit in, so this relative group system algebra fit into the group system algebra of G and the suspension of the group system algebra of gamma. So if you spell out the long exact sequence associated to this exact sequence, short exact sequence, then you see the relative group system algebra like sits in the middle. So K theoretically, this is the right object. Okay, so now I would like to introduce some kind of high index at infinity. So let's see. So let's start with a non-compact manifold and have an increasing. Let me introduce this concept of exhaustion. It's an increasing sequence of compact subset, and so we want them to get fatter and fatter. So that's this condition here. Okay, so let gamma to be the fundamental group of the entire manifold then, and GI is the fundamental group of the complement. Okay, so the high index at infinity is defined to be an index in the inverse limit of this sequence of relative group system algebra. The definition is a little bit subtle, but it can be done. Okay, but so also this is independent of choice of the exhaustion. I mean, K theoretically, not the system algebra might depend, but not this index. Okay, so of course, just like what Jonathan did, so we have a vanishing theorem. Okay. Okay, so we can actually, this looks very much like the group system algebra situation. So we can actually also propose some kind of Novikov conjecture at infinity, trying to decide non-vanishing of this high index at infinity. Now, this does not follow from the usual Novikov conjecture, but because there's a consistency, okay, if you go to try to prove this. And so it is a variation, but it does not follow. Okay, so what is interesting about this inverse limit is that there is a lim1 phenomenon. Okay, so this lim1 is just some invariant associated to an inverse limit of abelian groups. Okay, all right. So it's the co-kernel, or it's the co-kernel of this map of this infinite product of abelian groups to the infinite product of this sequence of groups, and that's the map. And so if we take an example like let P to be a prime, look at this sequence of an inverse system of abelian groups, then the lim1 is huge. So this is like, yeah, it's a very integral phenomenon. Okay, so it's actually, it also kind of justify all those like homologous stuff. If we do this everything rationally at the characteristic classes levels, and we lose this, what I'm talking about, all the information will be lost. Okay, so now what's interesting is this lim1 thing fits into this exact sequence of K-theory. So the K-theory of this inverse limit of relative group system algebra. So you would think that if there's a natural map of, you can restrict it to each of the group system algebras and consider the inverse, look at the K-theory, consider the inverse limit. If you have a K-theory element, you can send it to there. You might think that, whether it's 0 here in the K-theory of the inverse limit is the same thing as the inverse limit of a K group, but it's not the same. There's some lim1. Okay, so which means that any finite stage does not decide, these things at infinity. Okay, K-theoretically. Okay, so if it vanishes at any finite stage, then if this high index at infinity vanish at any finite stage, then of course there's a unique element coming from lim1. We can define this to be the so-called lim1 index. Oops. Yeah. Okay. Now, let me just quickly end my talk, like with the connection to Mitchell's compactness question. So Mitchell was asking that if essentially, this is for non-compact manifold. So whether you have a complete metric on a non-compact manifold, whether this can be decided by what happens on things on like compact subset, but there's a little subtlety how you formulate. This is how you exactly formulate this question. And so using this lim1 index, and Schmoltz, Zhang, and I are able to come up with examples that you can have manifolds and satisfying all the conditions, but it still does not have a complete metric on the entire space. I think my time is up, we need to use to build the space in a way that it demonstrates this lim1 phenomena, but there's quite a few subtle things going into it, like well, of course, surgery is an important part of the construction. Okay, so let me quickly mention that we also have some positive result if, like when the lim1 phenomena, like in this example, so the condition of one-tameness, then the lim1 phenomena disappear, then it's kind of, you have some positive result, assuming some additional the Gromov-Rosen-Rosenberg conjecture. Okay, all right. So we can modify Mitchell's conjecture. If in addition the lim1 index vanishes, then I think we are kind of we are optimistic that this probably is true. Okay, so I think I have the last slides here, which I will just put here. Unless someone asks any questions, and I will stop here. Yeah, thank you.